The following program is brought to you by Caltech.
Hello, I'm Judy Cohen, the Kate Van Nuys Page Professor of Astronomy here at Caltech and the Chair of the Faculty Committee on Institute Programs. It's a great pleasure to welcome you to tonight's Watson Lecture. But before I introduce the speaker, let me remind you that the next Watson Lecture will be on Wednesday, December 1st. It will be given by James Heath, who's a professor of chemistry here, entitled Personalized Medicine, Molecular Diagnostics, and Cancer. Tonight's talk is the second in two lectures about earthquakes and their impacts, the first of which was given on October 27th by Jean-Philippe Avouac. Forgive me if I've murdered his name, the director of the Tectonics Observatory, who presented a detailed study of the faults and earthquakes in the Tibetan Plateau, the Himalaya Mountains, and in Indonesia. Tonight's talk will be given by Swamithan Krishnan, who is an assistant professor of structural engineering and geophysics with a joint appointment between the Division of Engineering and Applied Sciences and the Division of Geological and Planetary Sciences. He's continuing a tradition of excellence in this field established at Caltech by Paul Jennings, our former provost and professor emeritus of civil engineering and applied mechanics, who helped to write many of the building codes for California, for the state of California. Professor Krishnan specializes in high end-to-end simulations of earthquakes and the responses of buildings and bridges using high-performance computing. He received a BS from the Indian Institute of Technology, an MS from Rice University, and a PhD from Caltech. Welcome Professor Krishnan to tell us about recreating the great Fort Tejon earthquake of 1857.
Thank you. Thank you, Judy, for the kind introduction. So today is a very special day for Caltech. Can anybody guess why? Apart from the fact that I'm giving a Watson lecture. Okay, so Professor Amnon Yariv, the professor of applied physics and electrical engineering at Caltech, has been awarded he was conferred the National Medal of Science by President Obama today. And this was obviously a great day for Caltech because it's an extremely coveted achievement, if you like. And he follows in the great footsteps of Carver Mead, a professor of engineering and applied science, and George Hausner, who is the father of earthquake engineering and who was a professor emeritus until he passed away a couple of years back. So the speciality about Amnon Yariv is that he brought two very important fields together, optics and electronics, to actually solve some extremely important problems in communications. And this has been the trademark of Caltech, is bringing fields together to solve some problems of huge societal impact. And today what I'm going to talk about is one such problem, and that deals with earthquakes and the response of the built environment to earthquakes. What you're seeing here, many of you may recognize, is a 10-mile stretch of Los Angeles starting from the west coast, from Santa Monica, to running along the 10 freeway. You see, all the way to downtown, you see pockets of tall buildings. It's basically a concrete jungle with pockets of many high-rise buildings. And this is now, we are approaching downtown. So behind you have the Hollywood Hills and you have the San Gabriel Mountains. And behind the San Gabriel Mountains is the Great San Andreas Fault. And this particular fault is the plate boundary between the North American plate and the Pacific plates. We are actually sitting on the Pacific plate. So in 200 million years, we will be actually adjacent to San Francisco, if you like. So what I'm going to talk about today is what we call rupture to rafter simulations, and this requires a tremendous amount of input from seismologists, from structural engineers and loss estimation experts, et cetera, et cetera. And so we actually collaborate with a number of people in this particular study that I'm going to talk about. We collaborated with Chen Ji from Santa Barbara, Dimitri Komatish from France, from Jeroen Trom from Princeton University, and then we have other faculty from Caltech, as well as Judith Mithrani-Reiser from Johns Hopkins University. So what is so special about the San Andreas Fault? Well, in 1857, there was a massive earthquake on this fault, and in 1857, the population of Southern California was 23,000. Today, of course, it's excess of 23 million, and counting. In 1857, there was a single newspaper in the LA area called the Los Angeles Star newspaper, and it reported that doors were slammed to and fro, water was turned out of bowls and pitchers, and in the river, the Los Angeles River, it had water back then, the water rushed violently to one bank and then back again. And this motion being repeated several times, back and forth like this. This, I will tell you, is indicative of what we call long period, large amplitude motion with long duration. What do I mean by that? I can explain to you for hours, but then the Mexicali earthquake happened, and I have a nice video for you to actually depict what long period ground motion is. So this is a hotel camera sitting on a post like this and looking at the swimming pool near the border. And the earthquake happens, and I'm going to play the video for you. So this is the first high frequency waves that are getting to the pool, to the hotel area. And watch that, notice that nothing happens to the water. It stays fine to this high frequency shaking, right? The pole, on the other hand, which is very stiff, on which the camera is mounted, it's going crazy, it's going wild, right? That's stiff, and it responds to high frequency motions. But after that, the long period motion starts. The slow motion. Now watch what happens to the water in the pool. It's going to go boom, whoosh, 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 whoosh. Right? So it's now draining out. This is an example of what happens to, so the big body of water is a long period system that responds to long period motions. It takes a long time to go back and forth like this. And these long period waves come after a while, and they drain out this particular pool that's trying to drain it out. And the same thing presumably happened in 1857. Well, what does it do to our structures? Why is this long period important? Well, I have a little model here. Think of this as your little house, and think of this as a high-rise building in LA downtown. So I'm going to simulate an earthquake here, and this is high-frequency motion that I'm going to simulate. The earthquake starts, the high-frequency motions come in. Right? So it's this guy. That guy doesn't care about the high-frequency motion. He's just staying where it is. He's sleeping around, right? So, and then the long period motion comes in. Look at that. It's going to knock me over. So that's the difference between high frequency motion and long period motion. So the long period, large amplitude motions selectively excite my tall buildings, my long span bridges. These are long period structures, and these long period motions selectively excite these long period structures. So what we want to understand is, we have today, back in 1857, there were no tall buildings or anything like that. And so today we have many tall buildings, excess of 700 tall buildings in the LA area. And the question is, how would these tall buildings respond? So we do what we call simulations. Firstly, let's try to understand, why do these long period motions occur in the LA area? Well, for that, you have to go back to the geological setting of the LA region. So what I'm showing here is the Los Angeles basin. I'm going to define a basin in a moment. So you see, this is West LA, this is downtown, and we are sitting somewhere here in Pasadena. And all around us, we have stiff mountains. The San Andreas Fault, the plate boundary between the North American plate and the Pacific plate runs like that, takes a big bend north of the San Gabriel Mountains, and then takes a bend further like that, going south toward the Salton Sea. We are all around, we are surrounded by very stiff rock mountains, Rocky Mountains, let's call them. Not really Rockies, but they're basically very stiff rocks. And in here, we have a very deep sedimentary basin. What's a sedimentary basin? Well, it's like what you have when you have rivers flowing, all the, various weathering activities by wind, et cetera. They weather the mountains, and all the sediments come traveling down into this basin, creating a huge deposit of softer sediments. I'm going to show that to you in a moment. So if you take a cross section, if I'm able to cut through the earth here, so this is BB. I'm going to cut through with a knife called B prime, right? So B prime, and I'm going to cut through here with a knife called A prime. And what I'm showing you is the cross section here. And if you notice, this is the Los Angeles basin. And what you're seeing here is, in this scale, is the velocity of the P wave. The P wave is this body wave. If you've thrown all of us have played with pebbles, throw a pebble into water, and then what happens? You have these gravity waves that travel out, right? So the particles, so the pebble hits the water, and then the particle starts jiggling, and they keep knocking each other like this, but the disturbance, right? So there is this knocking, but the disturbance is traveling, and that's a P wave, okay? That P wave is the most efficient way of transmitting energy from one particle to the next, and transmitting this energy, this radiated energy. That's the most efficient way to transfer these motions. So they are the fastest traveling waves when you have earthquakes, right? So and that P wave is extremely slow. This red here indicates very slow motions compared to the green regions, which are the mountains. So whenever you have mountains, stiff rock, the wave travels real fast. It just goes through it. But when it comes to these sediments, right, the wave slows down. It wants to take its own time, and it does this, right? It's doing that kind of motion for a very long time. So that's what the sedimentary basins do, is that they trap a lot of energy in there, because energy comes into these basins and just sits there. Doesn't, it goes very slowly out. And so that trapping of energy is what leads to this sort of long period motions. And have you seen this kind of trapping of energy before and leading to some damage to tall buildings? Many of you would have known about the 1985 Mexico City earthquake. Turns out Mexico City is actually built on a dried lake bed, right? It was built on a dried lake bed, which means it had a huge sedimentary deposit. So this earthquake happened 50 kilometers away offshore, right? Big earthquake happening, and then the waves start coming in. These high frequency waves, they get attenuated very quickly. They don't go too far. They just get attenuated 50, 60 kilometers, and you don't see them anymore. But these long period waves, they have energy that can travel over long distances. It turns out these waves came in, and they came into this lake bed, and the lake bed had a certain characteristic to it. It had a certain depth and a certain soft material property that ensured that it started resonating like a bowl of jelly. So if you shake a bowl of jelly with the right kind of frequency, if you like, then you will get these huge jiggles. If you do extremely fast, then you may not get much out of the bowl of jelly. It's similar to that. These particular waves, these 2-second waves, came in, and they started getting amplified by the dried lake bed. And 2 seconds, it turns out, corresponds to the natural period of these buildings. These buildings like to resonate when it comes to a 2-second wave. And there was this big 20-story building that actually collapsed on top of a 14-story building, and all hell broke loose over there. Right, so this is the kind of motions that we can see, and this is the kind of effects that we can see in, when you have a distant large earthquake coming into, sending waves into a sedimentary basin. And this particular building, even though it did not collapse, is out of plumb. You see, it's not vertical anymore. And these tall buildings obviously depend very much on the vertical transportation system, the elevators. And if the elevators become unusable, that's it. The building has to be retrofitted, and there's a tremendous business interruption associated with it. Okay, so at Caltech, we have developed many tools. Professor Jeroen Tromp, who's now at Princeton, his group developed many tools to do seismic wave propagation studies. So what I'm going to show you is one such study. This is a very small earthquake. It happened in Palm Springs, magnitude 3.9 in 2005. The earthquake will originate somewhere here. This is to set your bearings right. This is the LA basin. This is Los Angeles. So there is the little earthquake that starts, and you will start seeing the waves propagating into the LA area. There you go. So it's a small earthquake. That means it's almost like a little bomb that's just set off. And it sends the first initial waves are what we call the P waves. And notice how the P waves, so I'm going to pause it there briefly. So this is a P wave, right? So that's the fastest traveling wave. And the separation between the P wave and the S wave keeps growing. Why? Because the S wave is a wave where the particles are moving like that, but the wave is propagating in this fashion, right? So the P wave was particles moving like this, and the wave propagating like that. The S wave is particles moving like that, waves propagating like this. Right? A much slower wave. And so there is a separation between the P wave. The P wave likes to travel faster, and it just goes real fast, and the S wave stays back. And it turns out that the S wave is very damaging. It's much more damaging to structures than the P wave because the P wave is high frequency. And high frequency waves don't actually do much damage to structures. In any case, so the energy now, the P waves have come in. So what happens? Look at this. All of a sudden, the energy sort of out here, right, in the desert and in these mountains and so on, the earthquake is restricted to this, right? The shaking is restricted to these waves. The waves are gone. But observe what happens in the San Bernardino Valley area, in the LA basin. The motion lingers on. In the Salton Sea, it's much more prominent. The initial P wave is gone, right? It's out here. But look at the ringing of these what we call the sedimentary deposits, right? So they keep shaking for a very long time, well after the main initial S wave and the P waves have passed. And these are surface waves that have created surface waves and what are known as Rayleigh and Love waves that keep shaking the bowl of jelly, if you like. And that's what we are afraid of. Right? Or maybe we are not. So what do we need to do these kinds of models, right? So we are now, I just showed you a model of seismic wave propagation. Well, what you need to do is firstly, the way we actually, we have to have some information about how fast these P waves and these S waves travel in the Earth material, right? So we need to know something about the Earth structure. And then we need to be able to build a computer model. So we take the Earth structure, chop it into little blocks, what we call finite elements, and then we can now knock on this little piece here with an earthquake, and then that little piece will transfer, there is a solid block there, and it'll expand, contract, et cetera. They'll contract perhaps, and then it'll transfer the disturbance to the next node, and then that will transfer the disturbance to the next node. And so you can now propagate these disturbances through these Earth models. And so we now have these abilities to, we have actually have a decent understanding of the velocity structure, how fast these waves propagate in the Southern California area, and we have computer models that's happened in the last 15 years, that high-performance computing has enabled us to build extremely complicated, very detailed, large-scale models spanning thousands of kilometers. In fact, on the global scale, we're able to build these computer models and look at do seismic wave propagation studies. So how do we, the first question that one must ask is how do we validate these studies, right? So what we obviously do is we take small earthquakes that have happened, so regional earthquakes. In this case, this is a magnitude 5.1 earthquake. We sort of bin the data, we collect all this data, and then we bin it into two halves, take one half of the data, and do an inverse calculation about what happened on the fault. How did this rupture happen, right? That's called a seismic source model. And then we take that source model, we just initiate the earthquake. how much movement occurred on the fault, at what point in time did the fault rupture, how fast did the rupture occur. We impose all those conditions on the fault, we generate the rupture. And then we compute what happens at a variety of seismic stations in the LA area. And we then compare the recorded motions versus the computed motions. And what I'm showing here is the validation of this by observing that these recorded motions, which are in black, are match quite well with the computed motions match quite well with the recorded motions. The largest earthquake that we have had in this area is the Northridge earthquake, as you all know. At least that's been recorded quite well, the magnitude 6.7 Northridge earthquake. So what is the difference between these small earthquakes and these large earthquakes? Well, small earthquakes rupture a very small portion of the fault. Large earthquakes instead rupture a large portion of the fault. So the Northridge earthquake ruptured roughly 30 kilometers by 30 kilometers of the fault. And what you're seeing here is the amount of slip that occurred on the fault. Right? So that red spot there is a big slip. It's 2 meters of slip. 2 meters of slip is from here to here. Right? So that's the amount that the fault slipped at that particular location. So pretty big slips. Right? So that's the amount. And then what you're seeing here is we actually did a simulation of this earthquake to continue our validation process and compare our computed seismograms. So seismograms are these accelerations or displacements or velocities over time. How a particular point moves in time, shakes in time, is what this trace is telling us about. Right? So we compute these seismograms, and then we compare them against real data. And as you can see, for the largest earthquake in this region, we do quite well with our simulations. There are differences, and that's the limitation of knowing our limitations of our knowledge about the velocity structure, how fast these different waves travel through different parts of Southern California. So while all these exciting things were happening in the seismology side of things, the Northridge earthquake happened, of course, as I mentioned. And the Northridge earthquake brought along every earthquake has actually brings along a new moment among structural engineers, right? So this was an moment for structural engineers because, in 1971, the San Fernando earthquake happened, and then the moment was about concrete. We realized that we have to detail concrete very differently. We have to confine it. Otherwise, it's simply going to just fall off and fall all over the place. And after a couple of cycles of shaking like this, it'll just simply collapse. That's what happened to Olive View Hospital. After the Northridge earthquake, we thought, well, before that, we thought steel, right? It's metal. If you put together a steel building, it's going to be very ductile. You can take it take a wire and then steel wire, take it through many cycles like this. It will not snap. It will be able to sustain many cycles of motion back and forth before it actually fails. Well, that's all true, except that the chain is only as strong as its weakest link, and the weakest link in this case turns out to be what are known as the welds. So the beams were starting to be connected with welds. In the past, they were connected by rivets, but somewhere along in the 70s, it switched to weld. When welding technology became a common practice, these welds, it turns out that they were not ductile. The material was not ductile enough, and furthermore, the kinds of construction, the way it was being built, they started introducing lots of defects, little micro defects in the weld material, and it was creating lots of little notches that would lead to stress concentrations, and these stress concentrations lead to little fractures. Whenever you have a cyclic motion, it leads to fracture. And then that fracture, once it starts, it finds its way. It finds its way through beams, through columns. So you can see all kinds of fractures happening in the columns and in the beam. So this is in the column, this is in the beam, and so on. So we found that these kinds of fractures started happening. Well, and then what do engineers do? Well, okay, this is a great opportunity for us to learn. So let's go back and start building computational models for these. And that's what we did. It was the right time because high-performance computing was just coming into big business. And so we started building computer models to simulate the kinds of failures that we saw in the Northridge earthquake. Right, so and here is a model, 3D model of a building. And what do? Well, we subject it to an earthquake. So we in this particular case, this is a 20-story building. We subject it to an earthquake that was recorded in Iran. Okay, so you can see the motions have started now, and the building starts twisting, going back and forth. Why is that? Well, in this particular case, there is the lateral force resisting system is asymmetric. It has two nice frames in that direction, right? Two beam column, nice rigid frames on that face and on this face, but it turns out it has only a one rigid frame in this direction here. And so it puts the center of mass, which is right at the middle, away from the center of stiffness, which is out there. And so that starts doing a dancing sort of a twisting motion. So it's these kinds of simulations that we are now able to do following the Northridge earthquake, the lessons learned from that. After a simulation like that, what you can do is you can disassemble the structure. So in this particular case, we took this particular frame out and we quantified here the extent of damage that occurred in the beams and the columns and joints and so on and so forth. So we are now able to say how much damage will occur in a big motion, in a big earthquake, in each of these buildings. Well, we still have to validate these models, just as in the earthquake situation. And the way you could validate these things is, well, suppose you have a very simple component. So take a beam, and then you apply a load, a cantilever beam, apply a load to it, keep pushing on it at one end, and then you measure sort of the horizontal displacement and vertical displacement. This is an easy problem mathematically to solve. Right? It's easy to mathematically solve. You can sit down and with a notebook and pencil and solve that, and then you can do a comprehensive sort of computational analysis of the same thing, and then you can compare your analytical solution to the computational solution to the analytical solution, and we do that. But you could also build component models in the laboratory, and that's what many academics do. They build beam column assemblies, right? So a beam and a column, right, in a laboratory, and then they hold it up, and then they start shaking, if you like, the end of the beam. They apply a cyclic displacement back and forth, up and down on this end of this beam, and then, so this is a cyclic sort of displacement over time. And then you can compare, you can observe what kind of stresses occurred at this joint, and you can plot the stresses that occurred at the joint. So the material may yield, and you start to see this is the end displacement versus the force that you applied. And if there is no material yielding, then it would be simply a straight line. Back and forth, the force would be proportional to the displacement, or the displacement would be proportional to the force. But when material starts yielding, then plasticity sets in, and you start seeing, well, disproportional increase in displacements with a small increase in the force that you apply. And so we are able to now take our computational models and verify them against these component experiments. And here is something to wake you up, in a sense, if you're not sleeping, or if you're sleeping already. This is a shake table structure. So what I talked to you about earlier is a sort of a component test, a single beam and a single column going through these motions. What I'm going to tell you now is that we actually have these big shake tables. There is a big shake table in Japan. There is a big shake table in UC San Diego, outdoor shake table. So you build a building literally on top of these shake tables, and then you subject it to get it going in a big earthquake, right? You start shaking the shake table. And then you can then put sensors all over the building and measure what's happening to the building. And that's what happened here in this case, and we were part of a blind analysis contest. So they just told us how they were going to shake this building. They gave us the building information, and then they told us, okay, now you guys do your modeling, tell us what's going to happen, and then we'll compare our results. So that's what we did here. So this is an animation of that. There's a movie of that. So the earthquake has just started. I've started it on both of these. This is the experiment, and this is the model. Observe what happened here. There was a first-story failure, if you like. The building collapsed with a first-story mechanism. And we are able to replicate that mechanism quite well. We were actually very close to the timing of that particular big failure occurring. We were very close to the second decimal in the seconds. So that's how we are validating our numerical models. Now to tell you okay, so now I've told you we have great models for computational seismic wave propagation, right? We have great models for buildings. Now the next thing to do is just put them all together. And the way we put them together is, well, let's recreate the 1857 earthquake, right? So this was an earthquake that happened. We have some information about it. Paleoseismologically, so paleoseismology is where you would go in and dig trenches across the fault and sort of look at what happened, date events on the fault and how much slip occurred in each of those faults. So they've done that. Professor Kerry C. was a pioneer from Caltech, who spent many of his years looking at the San Andreas Fault, and he was able to put together a picture, a snapshot of what happened in the 1857 earthquake, how the fault moved, how much displacement occurred, with what velocity did the slip occur, and with what, actually he couldn't say much about the velocity with the slip occurred, but definitely he talked about the amount of slip that occurred. So some of the other factors about how fast the rupture occurred, we have to sort of put them in there probabilistically. And how do we do that? Well, before I tell you that, what we are doing here is that we are generating the earthquake. This particular earthquake is deemed to have started in Parkfield. So after digging all these trenches, he said, well, I think that the earthquake originated in Parkfield, and it terminated somewhere in Wrightwood, north of Southern California. And so what we want to do is to recreate that earthquake. Our region of interest is this populated region, is this region where we have many structures. So in this region, we actually place 636 analysis sites. These little triangles are analysis sites where we are measuring, we are computing the ground shaking. We are then going to place tall building models at each of these locations and study their response of how they would behave, would they collapse, et cetera, at each of these little triangles, right? And they're spaced at roughly 3.5 kilometers apart. Okay, so as I mentioned, so we know something about how much slip occurred in that earthquake, but we don't know a lot of other things. So you need to be able to specify how the slip occurred, how much occurred, at what times did it occur, how did the fault move, and that's called a seismic source model. So one way to actually figure out, impose a seismic source model is by taking inferring what happened on a geometrically similar fault, right, in a historical earthquake, and then mapping that information onto the San Andreas Fault. Luckily or unluckily, there was a big earthquake on the Denali Fault in Alaska in 2002. So in 2002, there's a 7.9 magnitude earthquake on the Denali Fault, which runs along the along the coast of Alaska, and that fault is actually geometrically very similar to the San Andreas Fault. It's almost vertical dipping, and it's also right lateral strike-slip fault. The strike-slip fault is, if you saw the earlier cartoons, is where the fault motion is in this form. Right? So there's a fault plane, and one side of the fault, the ground moves in one direction, and the other side it moves in the other direction. Right? And right lateral simply means if you're standing like there, the opposite side is moving to your right. And the San Andreas Fault is essentially a right lateral strike-slip fault, vertically dipping. The Denali Fault was similar. And so we recorded a bunch of seismograms from the Denali earthquake in 2002. And what we did was we said, okay, so we will now infer what happened. Using that data, we inferred what happened on that fault. And then we map that seismic source onto the San Andreas Fault, with rupture initiating in Parkfield in Central California, rupturing down south 290 kilometers. So, well, what happened in the Denali earthquake is, this is a map of how much slip occurred. And what you're seeing here is 12 meters. That's right, so it's 12 meters of slip at depth. So at a depth of 10 kilometers, you see 12 meters of slip. That's from here to, twice of that distance. Right? So huge slip. If you're standing here, you would be standing at the fault itself. On the surface, right, the slip was of the order of 7.5 meters, still pretty big. So huge slips that were seen in this big earthquake, and that's what we anticipate in a big San Andreas fault earthquake. We said, okay, let's map it down to the Southern California, let's start the earthquake, and so what you're seeing here, observe this clock here, you're going to see the San Andreas fault come tearing, right, rupturing like that. The motions are now arriving in Santa Barbara at about 58 seconds, right? And the very strong intense motion in the San Fernando Valley and in the Los Angeles basin. And these motions, the earthquake, the main waves have passed, but look at the ringing, the very strong reverberation in the LA area for a very long period of time, and I'm now looking at 3 minutes, right? So very strong intense motions, at least 1.5 minutes of very strong shaking. What you could do is, well, that tells you qualitatively, right, how these motions occur. But quantitatively, what we do is we create these maps of peak velocities and displacements, right? So the Earth can move here, there, and this way, in which way, like a drunken man's walk, right? So it can move in any which direction during an earthquake. And so we have to break it down. Break it down into 3 components. We break it down into east-west component, north-south component, and then the vertical component. We break it down into 3 components, and these are the maps of the peak displacement. So you take this point here, this particular triangular site here, it would have had roughly 0.8 meters of slip. So I'm going to blow it up a little bit. Look at the east component here of the velocity. What you're seeing here is 2 meters per second. So the scale here is red is 2 meters per second. Green is roughly 1 meter per second. So in the San Fernando Valley, extremely intense motions. Why? Well, because the energy is being directed towards you. The earthquake was propagating north to south, and it was what was right in its path? It was the San Fernando Valley. So it sent a lot of energy into this basin. So there is a nice basin structure here, there's a nice basin structure here, and there's a nice basin structure here. And sent a lot of energy into these basins, get trapped there, very intense motions, 2 meters per second velocity. So in 1 second, you're going from there to there and shaking back and forth for a pretty 1.5 minutes. Imagine that shaking intensity, it's pretty strong. And in the LA downtown area, the peak velocity was over 1 meter per second, still extremely intense, right? And the displacements have a similar ring to them in terms of numbers. It's 2 meters of slip, 2 meters of ground motion here, peak ground motion, 1 meter of peak ground motion in the LA basin. Very strong and intense motions for a very long period of time. So you're moving like this, like that, back and forth, right? Well, we have the ground motions now, so we can exactly say how these points are moving back and forth in space and in time. What we do is next, we take building models. Right? And so here are 2 building models that we worked with in this particular study. This is an 18-story building that's actually an existing building in Woodland Hills. It's even today, it's existing there. It had these connection damage during the Northridge earthquake. So what happened during the Northridge earthquake was, after the earthquake, people came back to work. The building looked fine from outside. They tried the elevators wouldn't budge. It turns out that they called the surveyor, and then the surveyor said, well, the elevators are out of alignment. It turns out that this building was tilted by just 6 inches. 6 inches is this much, right, over a height of 75 meters, so 18-story building. And that can throw your elevators out of sync. And then the building had to be opened up to understand exactly how much damage occurred, and it turns out it had all these connection fractures. So quite a susceptible building, I would say, right? Designed according to the 1982 building code provisions. And then what we did is we said, let's see, well, we have improved the design codes quite a bit, thanks to some of the work that Professor Hall and Professor Heaton and Professor Iwan did at Caltech, that the building codes were significantly improved after the 94 earthquake. And so they came up with the 97 UBC, Uniform Building Code provisions, and we have a new building. So we redesigned that building to these modern provisions. And well, what is the difference? Well, in this particular case, you see only, this is the existing building, right? So this is a floor plan, if you like. These are the beams, and the main beams of the lateral force resisting system. You see 2 bays plus 2 bays in each direction. So in that direction, you have 4 bays of moment frame. In this direction, you have 4 bays of moment frame. If you look at the modern building, that's got 8 bays of moment frames. Oh, it's much more sturdy, if you like. It's much stronger, if you like. It's a very different kind of building. The modern codes have ensured that these buildings are likely to be much stronger. So what we did was we took these 2 building models, one an existing building, a surrogate for an existing building, another a surrogate for a modern building, and placed them at each of these 636 analysis sites. And then we ran through our computer models. We sort of looked at the shaking, we put the shaking into those, each of those models, and then we looked at how the structure would respond. Well, what you're seeing here is the response of the structure, one particular parameter that tells you how close the building is to collapse, right? So that's what I'm plotting here, that parameter, but that parameter for the existing building and for the modern redesigned building. Okay, so for the existing building, right, so this is the damage that is concentrated in the top third of the building. That is the damage concentrated in the middle third of the building. And that is the damage concentrated in the bottom third of the building. Well, why is this important to distinguish between where the damage occurs? Well, as you saw in the World Trade Center, right, the lower the damage concentration, if the damage is concentrated in the lower stories, it's carrying greater number of stories up above, so there is a greater chance of a greater number of stories pancaking one on top of each other. So it is very serious if you have significant damage in the bottom third as opposed to the top third. So if the damage was localized in the top third, well, then the risk is much less of the whole thing, structure coming pancaking down. So it turns out that in both these cases, the damage is localized in the middle third and in the bottom third of these structures, both buildings. And furthermore, if you look at, I'm going to blow up this particular existing building response in this region, and what I've plotted here is that damage measure. IO here, I've given you some parameters to sort of judge as to where. IO would be immediately occupiable. In other words, if you have a blue response, like here, if the building was located in San Pedro Hills or someplace like that, right, fictionally, then it would be immediately occupiable after the earthquake, no problem, right? So LS is life safety. So if you're in this light bluish range, in this regime, that means there would be very little probability of loss of life in that building after the earthquake or during the earthquake, right? So if you're in the green regime, well, you may have some loss of life, some life safety problems, but you've prevented collapse, right? So green is actually not so good. Green, the color is good in all springtime, but it's actually, in this particular scenario, green is already on the verge of instability, if you like, right? So it's collapse prevention. And beyond this green point, there is a substantial risk of collapse. And what I'm showing here is that much of this, wherever you locate this existing building in the San Fernando Valley, it is toast. It is, right? And in the West LA area. So this is the original movie that I showed you was from Santa Monica going to LA downtown along the 10 freeway. Lots of high-rise buildings in that range. So some, if this earthquake were to occur in the way we are predicting it, in this particular simulation, well, it would be bad news for that existing building if it does exist there, right? And the redesigned building does much better comparatively, right? It's still all this nasty red stuff, because of the intensity of ground motions. Like they say, if I would like to say, you can give me any building and I can give you a ground motion that will collapse it. There is no building that is earthquake proof, right? So these are extremely intense motions, and even if I boost this building so much, yet in some locations, if you locate that building, it will still collapse. And that's what we are seeing. But thankfully in LA downtown area, you see now we are somewhere between LS and somewhere between life safety and collapse prevention. But collapse is generally prevented. And I'm going to show you a movie now, sort of visualize how this thing happens. So if I place these 2 buildings at Northridge site, I'm going to show you what happens to those 2 buildings, right? So I talk about these maps and say, well, it may collapse or may not collapse. You're going to see what's going to happen here. This is a very busy slide, so don't worry about all the busyness here. What I'm going to say is that this is the existing building. That corresponds to the redesigned building. This is the earthquake ground shaking. So the displacements, the sort of the waveform of the traces of how the ground shakes at Northridge site, right? And the animations are scaled up by a factor of 5 to give you, a real feel for what this earthquake does, right? So there is a system clock here telling you about the time, right? So the earthquake starts, right? Initially, both buildings are doing fine, right? So here you can see the roof response of this building and the roof response of that building. For the first 20 seconds, this building is able to take it. It's able to keep itself coherent, homogeneous, nice, and not much damage. At about 35, 40 seconds, when this big wave comes in, right? So actually the big wave, one of the big waves already passed, but subsequent shaking, the big wave has caused enough damage, but subsequent shaking, this guy starts twisting. It has an inherent tendency to twist, this particular existing building, and in that twisting process, it actually ends up collapsing those few stories. Observe that the collapse occurred in some stories, not exactly at the base, but somewhere up above. Right, so this is a characteristic feature of these buildings. The redesigned buildings performs much better. Right, so it doesn't really collapse, but if you look at this, it never really came back up to plumb. Right, so it had some damage here, because of which the structure kinked, and then it stayed there. It just oscillated like that, and then like this. Right, so at the end of the day, this looks like the Mexico City building that I showed you a photograph of earlier, where the building is tilted after the earthquake. So perhaps the elevators would not work. This is the amount of roof permanent tilt, right? So where in the existing building in the Northridge earthquake had only 6 inches, what you're seeing here is the existing building having 1.5 meters of permanent offset, roof being tilted, in this direction or in that direction. The direction doesn't really matter. Once it's tilted, it's tilted. So the redesigned building, again, performs much better than the existing building. But what I'm saying is that we are now able to quantify how bad the situation is going to look or how good the situation is going to look after this earthquake. What we have subsequently done is we said, well, okay, so we looked at how the structure responds. But really, somebody wants to know how much damage is there, what kind of expenses am I going to face, how much is going to cost to repair this building. It turns out to replace this building could cost $72 million. Okay, 20-story building, roughly $72 million. And what I'm showing here is we actually populated this building with all its contents, right? And its structural system and mechanical system, electrical system, everything else. And then we sort of estimated the cost associated with, based on the structural response. We said, this is the amount of damage you're going to see to various systems. And then we estimated the cost associated with it. So what you're seeing here is that if the structure is in the sort of the magenta, beyond the magenta range, it basically means that your structure is totaled. You have to, essentially, you're better off replacing it. And what you're seeing is much of the region, this existing building, you're better off replacing it, whereas the redesigned building does much better. Okay, so I talked about a north to south rupture, so where the earthquake was coming towards you. What we said was, what happens if the earthquake actually started in Southern California and the rupture was directed away from you, right, towards Central California, towards Parkfield. So we took the same magnitude earthquake, right, the same earthquake basically, and just flipped the source model and allowed the rupture to go from south to north. So this was a north to south, this is a south to north. And what we see is that the south to north rupture ends up giving you much, much less intense motions. The north to south was when it came towards you, it shed a lot of energy towards you into your basin, and that's called rupture, that's called directivity, the effect of directivity. If the rupture is in the direction, if your structure is in the direction of the rupture, if the rupture is coming towards you, it's going to hit you with a big, you would have all heard of Doppler's effect. One could consider that as an analogy for this, right? So you're going to see a lot of energy coming at you if it's a north-south rupture, whereas if it goes from south to north, much of the energy is now focused into the central valley, and the farmers are going to take the brunt, right? So, And if you now compare the structural responses, so what I showed you was ground motions, and here I compare the structural responses. So this was the original north to south rupture scenario for the existing building and the redesigned building. And this is the south to north rupture scenario for the response for the south to north for the existing and redesigned buildings. And you can see blue, right? Hunky-dory, no problem. It's all, we are all in the immediately occupied regime. So it's the same earthquake, magnitude 7.9, same segment of the fault rupturing, right? All we changed was, and in fact, the same slip distribution, but then we flipped the slip. We put some big patches of slip away from the LA region, right? And then we allowed the rupture to go away from the LA region. And that changes the whole scenario. That gives you, yin and yang. So to conclude, right? So to conclude, pray for the south to north rupture. Now, what I'm trying to suggest is that the conclusion that I would like you to take is that I hope I've convinced you that high-performance computing has really thrown open new horizons in seismology and earthquake engineering. Right? We are now able to do these realistic rupture to rafter simulations, so rupture of the fault to rafters. Rafters were the beams and so on in these buildings. We're able to do those simulations, and these are becoming possible. And they're giving us some really key insights into how earthquakes affect the built environment. So in the past, traditionally, structural engineers have built something, and then they wait for a big earthquake to happen, and then they watch, and then they learn, and then they change their building codes, and that's how we used to operate. That process is extremely slow because earthquakes take their own sweet time to come, right? So these modern tools, what they allow us to do is to be proactive in earthquake hazard mitigation by actually being able to say, well, if this earthquake happens, these would be the kinds of failures that we would see, and these are the kind of measures that we must take today in order to ensure that we have a better result at the end of the day, from keeping a disaster from becoming a catastrophe. Well, if you didn't get all of that, then at least get this: the difference between a scientist and an engineer. So I'm here talking about science, engineering, and all that. Right? What is the difference between a scientist and an engineer? This is the office of my colleague, Professor Tom Heaton. He's a scientist. He has a clear mind and a cluttered office. Right? So that's a scientist. This is my office, clean office, cluttered mind. On that note, there are many people who I've collaborated with over these past years, and most importantly, my students here, they're sitting, at least some of them must be out there, or some of them are sitting doing their homeworks or research. So I have to acknowledge my students, my collaborators, my mentors. There are many people out here, and of course the funding agencies, without whom we just cannot do these kinds of beautiful research. Thank you.